In discussing extrasolar planets and exoplanets as a byproduct of star formation, uh, that's fine, because that relates to what we were talking about this semester. But it also relates to, in the textbook, Chapter 8, which is the formation of the solar system, because that's where your book actually talks something about extrasolar planets as well. So again, we're kind of bouncing back and forth in the book here a little. In order to describe how planets form, we want to do this scientifically, have a theory of planet formation that explains what we see in our solar system. And that's going to be a key sort of thing to explain that. And what we notice is when we look at other planets, they don't all match what we see in our solar system. So that means that we don't fully understand everything there is to know about planet formation. And so this is still an active area of research. When we look at our solar system, I kind of like and hate this graphic right here. I found this graphic as a free downloadable file that teachers can download and print out to hang in their classrooms. A great elementary school graphic for showing the solar system, because it shows all the stuff that's in the solar system. You know, we've got the sun, we got planets, we got asteroids, we got comets, and all kind of things. That's nice, except everything's wrong. Okay, you've got first of all, we don't really consider Pluto a planet anymore, and the sizes of everything is wrong, and the spacing of all the orbits is totally wrong. The order of them is okay, but other than that, everything else is wrong. So I both hate it and love it. I love it because it's actually kind of a pretty picture here, and great for hanging up, and then I hate it because there's so much wrong with it. Really, from your textbook, this is really from chapter 7, but just to flesh things out, this is kind of what the orbits really look like. And that is that if you look at these orbits, the inner solar system, Mercury, Venus, Earth, Mars, are all crammed close together. The outer solar system, Jupiter, Saturn, Uranus, and Neptune, are all spread out. And then Pluto's orbit doesn't even fit, because all the other planets lie in a plane, and Pluto's orbit is wildly with respect to that. The other thing that we notice about the solar system is that we have 4 small rocky worlds and 4 gassy giant worlds. The gas giants, Jovian worlds, are hydrogen and helium rich. In fact, they mostly are made of hydrogen and helium. And the smaller worlds are mostly made of rock. And so how does all this work? Well, the idea that clouds of gas really collapse to form stars goes all the way back to a fellow named Swedenborg, and he also was in thinking that these clouds also collapse to form planets. Immanuel Kant here is famous for being a philosopher. He had some great work on philosophy of science, and in his work, he also investigated this idea and put it into a more scientific footing. Swedenborg's ideas were nice, but they weren't really super scientific. They were just basic conjectures. Kant actually started the idea of putting these things into hypothesis and testable sort of way of looking at things, so you can actually go out and set up a telescope and look. So that became the first step of it. The mathematics of this really came into play in the 20th century when going through the math of how all this works, you realize that yes, gravity does make things fall together. Centrifugal force, as this thing falls together, makes it spin, and when it spins, you get this disk, and then the disk will flatten out. That would explain why all the planets, would be in a disk. And they'd clump up in there. And the way they clump up, mathematically, you can see that a big clump, in other words, a big planet would have gravity that would keep any other planets from nearby happening. And so you say, oh, wait, okay, that explains why the gas giants don't have any planets near them, why they're so spaced out. The other thing is, mathematically, you say, well, if you look at what's close to the protostar up here, up close to the protostar is going to be warm, and so that means you're not going to have much icy stuff in there. Out far from the protostar, it's going to be cool, and you can get icy things mixed in with the rocky things. Well, that means you could possibly build bigger planets. So this idea mathematically naturally says that small planets form close to the protostar, and big planets form far from the protostar. And since the big planets are going to have enough gravity to disrupt the orbit of things near them, that means that the big planets are going to be farther apart. Well, this seems to describe a whole bunch of what we see in our solar system. This disk is all going around in one direction. It's going around the same direction that the protostar is rotating. All the planets go around the sun in the same direction that the sun's rotating. And the inner ones are small and rocky, and the outer ones are big. Okay, we actually believe that Uranus and Neptune are like half ice and half hydrogen and helium. And so this seems to fit very, very closely with our solar system to a degree. It's not perfect. One of the big problems they had in the mathematics of this process was that they could not explain the angular, what they call the angular momentum problem, is that the angular momentum of the sun is out of sync with the angular momentum of the planets. And so they couldn't understand how that sort of thing would work. But once they began to realize about those jets, the bipolar jets we talked about that give rise to Herbig-Haro objects, once they did that, they realized, oh, wait, this totally makes sense. Okay, that's why the angular momentum is the way that it is. Okay, so everything swirls up, and you get this disk, the accretion disk, and the accretion disk is surrounding the protostar. Okay, and if we look into nebulae where stars are in the process of forming, we see these little disks around these stars. Now, the thing is, when the protostar gets hot enough, the radiation pressure from the protostar will stop accretion. So that accretion disk quits accreting. But that disk hangs around for a while after it quits accreting. So as it hangs around a little bit, you'll have a disk surrounding this brand new protostar or even very young star. And that disk can then clump up. So they come up with a name for this disk. The name for this disk is a Proplyd. Now, you would think you would call it like a protoplanetary disk or protoplanetary nebula or something, except protoplanetary is used for something else. And so that name was already taken, and so they ended up coming up with a brand new word, a Proplyd. A Proplyd is the name that we apply to this disk, the remnant of the accretion disk that's surrounding a young star, and that Proplyd can then clump up and form planets. And so this is the beginnings of our study of how planets could actually form.